think you're good to go. The other way around, I think.
Like this.
Yeah.
That's it.
Mr. Kali, I'm sharing this session. Huh? Are you the chair? Okay, perfect. Water for you?
Thank you.
Some water for you. Okay. 5 minutes?
Yeah.
So 5 minutes before.
Yeah.
So,
45 minutes, including questions, right?
yeah.
Yeah. Good.
5 minutes before.
Yeah.
Not stopping, just saying that this is correct. So please.
All right. So, good morning, everybody. Welcome to the morning session of the last day of our conference. 3 days, so today is also a dance day, fine. So I'm welcoming you to invited talk of Professor Supponen of this department of DIMAP. It is Zurich. So Professor Supponen, so she's doing real fluid dynamics, real wet thing, and look at the numbers. So she's going to present some part of the work. The title is, well, it attracts attention, indeed, you remember. Visualizing the invisible multiscale and multiphase fluid dynamics. Please.
So thank you very much. Good morning, everyone. First of all, thank you so much for inviting me to talk at this conference. I'm a little bit of an outsider because I consider myself almost a pure experimentalist, but hopefully you can still learn something out of this presentation. To start with, what do I mean by invisible multiphase fluid dynamics? So by invisible, I mean something that is not visible to our eyes, and that can be many things. When the target is either too small, too far, too fast, or offers too little optical contrast. And these are challenges that we like to tackle experimentally. We're trying to look at things that are either too small, or they move too fast, they're too far, or they offer too little optical contrast. And by that, it could be in an opaque medium, or you might have dense clouds of bubbles or droplets or so. So we try to tackle those experimental challenges, and especially when they're related to multiphase fluid media, so bubbles and droplets especially. So the goals of this presentation they're twofold. First, we're trying to identify whether your simulations can help compensate some of the major experimental limitations that we face. So I've come to realize that experiments can't solve everything, that we also need numerical simulations. So maybe you can help with that. And also, hopefully, I will be able to present some useful techniques, experimental techniques that can help validate your simulations and for serving as numerical benchmarks. The physics we tackle in these experiments are typically related to acoustics and bubbles and cavitation in particular. So I'll try to explain why we are interested in these types of phenomena in particular. So we like to look at bubbles that are driven acoustically. Can I take this off? It's quite terrible. Will you hear me if I speak? Can you hear me like this?
Yeah, absolutely.
Yeah, thank you. Much better. So we are interested in bubbles that are driven with acoustic waves. The reason is that bubbles, because they have a gas core, they're compressible, and they will be very sensitive to changes in pressure in the surrounding medium. So if you have a high pressure, they will compress. If you have a low pressure, they will expand. And in particular, if you do this sort of periodically with subsequent oscillations or fluctuations of pressure, you have sinusoidal driving, for example, like in this illustration, then you can drive bubbles in periodic oscillations. And gas bubbles will have some sort of a resonance frequency, so at which the oscillations will happen at much higher amplitude. And that's an interesting feature that we can leverage by just having the right acoustic parameters to drive bubbles into radial oscillations. Essentially, this represents converting acoustic energy into flow motion, if you will, or radial flow motion, also translational flow motion. And at extreme cases, when the amplitudes are really high, you can make these bubbles collapse, and they can convert energy to really small single point. And then you can have phenomena happening like, well, rebounds. The bubbles will rebound. They will have several oscillations after the collapse. You might have emission of shock waves, so liquid compressibility becomes important, and then you emit these really high pressure acoustic waves. You can have thermal effects and even luminescence, which is light emission from collapsing cavitation bubbles. And this is because you're heating up the content so radically that it can emit light because of extreme temperatures. And you can also have high-speed microjets. This is when a bubble collapses in a non-spherical way. And both microjets and shock waves have really been sort of identified as the main damage mechanism causing so much erosion in hydraulic turbines or ship propellers, are the classic examples of hydrodynamic engineering flows where cavitation is harmful. Now what's interesting about this type of phenomena is, well, what if we could control them in a way that we could leverage and use them for beneficial applications? And there is quite a certain level of control you can have with acoustic waves. So for example, this is just the pressure profile of a shock wave that we can generate in the lab using lasers. And if you hit a shock wave to an existing gas bubble, you can make it jet in the direction of the shock wave propagation. And you can, so not only you can control the direction of the jet, but you can also tune the strength of the jetting based on your acoustic driving parameters, so the shock energy, if you will. And this happens this can be done at various scales. So I was showing a rather large bubble that's easier to look at experimentally, but also micrometric bubbles, it's about 50 micrometers in size, will show similar behavior. So it goes across scales, which is a very interesting feature we'd like to leverage. So this is what my talk will be about today, is mainly acoustic cavitation and bubble dynamics. And they are considered invisible because of the prohibitive spatial temporal scales. So they're extremely fast, and a lot of the phenomena we're looking at are also very small. So that's just very, very difficult to look at, and we're trying to push the experimental techniques to really resolve those dynamics in the lab. And of course, so we are spanning across scales. We're especially looking at microscales, but a lot of these phenomena are relevant in sort of a multiscale environment. And especially, we like to look at single bubble and droplet phenomena, but typically they are relevant. I mean, they form in clusters and clouds that are really, really complex, that we also tackle in the lab, but I'm only focusing on single bubble dynamics today. And here are just examples of there are cavitation bubble clusters in ultrasonic fields. And this is cavitation from shockwave lithotripsy. So when you have really high intensity shock waves generating cavitation. And the whole motivation behind this research is all these different applications, in particular in biomedical applications, where bubble dynamics, acoustic bubble dynamics and cavitation can be leveraged for beneficial uses. So these include drug delivery using microbubbles, bioadhesion and drug delivery through the skin, or transdermal drug delivery, lithotripsy using shock waves or high intensity ultrasound to treat kidney stones in the body. There are also applications such as ultrasonic cleaning, maybe one of the most relatable application is ultrasonic dental cleaning. So with the ultrasonic scalers, cavitation helps to remove dirt from your teeth. But we also have ultrasonic mixing, emulsification, homogenization, as well as water treatment and food processing. But really what I'm focusing, or our research mainly focuses on the biomedical applications. And today I'm mainly going to talk about the dynamics relevant for drug delivery. Right, so what's about microbubbles for targeted drug delivery? First of all, we look at what type of bubbles we're looking at. So microbubbles used for targeted drug delivery, or what we want to use for targeted drug delivery, are coated. They have to be coated because otherwise they wouldn't exist. So microbubbles at this scale, 1 to 10 micron, if they didn't have a stabilizing coating, they would immediately dissolve because of an enormous Laplace pressure. So they need a coating that stabilizes or neutralizes the surface tension, but also acts to prevent coalescence between bubbles, and also useful because you can attach drugs to them, so you can functionalize these bubbles, and then that's interesting for targeted drug delivery because you want to bring the bubbles with the drugs to the target's location. There are various ways you can make these bubbles in the lab. And they are also commercially available because they are used for contrast, for ultrasound diagnostics to enhance imaging contrast, medical ultrasound imaging. Then you inject these bubbles inside the blood circulation, so then they will circulate systemically inside the body. Then you apply ultrasound and you activate the bubbles into motion. So they would have these oscillations. And then the bubbles interact with the surroundings. So they interact with the blood vessel walls, endothelial cells, for example. They will cause in the right sort of operating conditions, they can yield sonopermeabilization. So they can increase the permeabilization of cells to drugs mechanically. This has been shown in vivo, and now also clinical trials in humans is ongoing for opening the blood-brain barrier. It's a very difficult barrier to open and where the drugs can go through. And also these bubbles can be used for other applications such as sonothrombolysis. So you're dissolving breaking blood clots inside the blood vessels. And also you can ablate cells directly. So there's again, we're talking about very strong violent events happening, or the mechanical stresses exerted by these bubbles to the surroundings that can then interact with the biotissue inside the body. So we first look into the acoustic response. What do these bubbles do as you excite them with ultrasound? So the way that we tackle this, or we want to observe this, is experimentally. We want to look at single bubble oscillations driven by ultrasound, and we use ultra-high-speed video microscopy to do that. So these bubbles at micrometric scale, they resonate conveniently at frequencies that are relevant to the medical ultrasound imaging, which is megahertz. So you drive them into the highest amplitudes at megahertz frequencies, but if you want to temporarily resolve the dynamics, the oscillations, then you need megahertz sort of range sampling. So that's what we do. So we built a microscope in the lab. We have a magnification of 200x, where we place a single bubble inside a test chamber. We typically use agarose gels that are optically and acoustically transparent, so we can drive them with the acoustic waves. Then we use optical tweezers. So this is with a laser to try to move the bubble away from a boundary, so that we have no interactions with nearby boundaries. Boundaries would, for example, change the resonance frequency of a bubble. So we use a laser to take it to move it away from the boundary, and then we activate these bubbles with sound waves. And this is the type of video we would typically get. This is at pretty high acoustic amplitude. We are not only getting volumetric, sort of spherical volumetric oscillations. The dynamics can easily become quite complex, because here, for example, we're starting to see deformations and shape modes and interesting dynamics, and then we look into detail. But first, to understand the spherical oscillations of these bubbles, they can be very well predicted and modeled with the Rayleigh-Plesset equation, if you're familiar with that. So that just describes the radial dynamics of bubbles as a response to changes in pressure. Works really well, especially for bare bubbles that have no coating. The problem with the coating is that they add some mechanical, they will have some, the mechanical properties of the coating will change the bubble response. And in our case, we use bubbles with lipid monolayer coatings. They could also be polymers or proteins, but in our case, we're using lipid monolayers. And that has to be accounted for in the modeling. So for that, we need to characterize the viscoelastic properties of the shell that we can add to the models describing bubble dynamics. And in particular, we look into describing, well, what is the surface tension and the dilatational viscosity of the shell. And so there has been several models proposed in the past. So initially, it was proposed that, well, we can just have an effective model parameter, effective constant surface tension and the viscosity describing the shell approximately. But of course, that violates, especially if you have a finite surface tension when the bubble is at equilibrium size. And here in the x-axis, I'm showing the expansion of the bubble. It's the radial excursion of the bubble. So when the bubble is at its equilibrium size, or in zero in this graph, the surface tension should be zero so that it can remain stable long term. Otherwise, it would dissolve. Like I mentioned, they stabilize. It should have a neutralized surface tension. So this is not okay. The better proposal was then to have a linear model where the surface tension varies linearly with the excursion of the bubble, so that the surface tension would be zero when the bubble is at equilibrium. But then it also assumes that the bubble can withstand compression when it's smaller than the equilibrium bubble size. A very good model was proposed by Marmottan almost 20 years ago, which was a nonlinear model, which allowed, or it doesn't allow any compression of the shell. So it doesn't allow any compression of the bubble, and the reason for that is that it buckles. So as you can see, even in the lab, we can see that when we apply high pressure, the bubble kind of becomes a bit of a prune. So clearly the shell buckles. It doesn't withstand any compression. And then at certain radius, the shell ruptures, and then it feels like there's no neutralization from the shell, or the surface tension is not neutralized by the shell, because it just, you break the shell and then it's effectively just a surface tension of water with gas. Okay, so surface tension model works really well. We use it, I think this model is a still effective model, but it does a pretty good job to get the overall dynamics. Problem is viscosity. Now, there's a lot of estimates of viscosity on sort of using single bubble dynamics. And there's quite a bit of differences what people are reporting. Here, there is viscosity on the y-axis, x-axis, the equilibrium bubble size. And for some reason, people have been reporting dependency on the dilatation of viscosity on the bubble size, which makes no sense because it's a surface material property. It shouldn't be dependent on the scale of the system. So many studies are reporting kind of this increasing trend, huge discrepancies, different types of trends, but basically that's what we have been at. Typical way to estimate the viscosity is following. So basically they get from single bubble dynamics the radial time response, the radius time curve. There's various techniques. One is imaging, like we do. Then you make a frequency sweep. So you have a single bubble, and then you vary the frequency of the acoustic wave, and then you get a resonance curve. So you get this kind of curve where the peak happens at the resonance frequency of the bubble. So you get the maximum response. So that gives you an idea of the elasticity of the bubble shell, but also the width of this resonance curve gives you an idea on the damping. So it's a bit like in a mass spring system. And the damping gives an idea on the shell viscosity. And that's exactly how they would do. They would use a linear model typically, so linear bubble dynamic, linearized Rayleigh-Plesset to get the shell viscosity. So the difference for us is that, well, instead we use the same thing, radius time curve, but we directly apply the nonlinear Rayleigh-Plesset model to directly infer this model parameter, shell viscosity is kappa S. And so the types of results we would get is, well, we first look at the radial excursion of the bubble. The graph here shows every dot is a bubble driven at a certain frequency, in our case 1.5 megahertz, and a certain constant pressure. And then we've tested bubbles of different sizes. And again, there is a maximum response at a certain size. So we have the resonance bubble size. But what we also see is that you can have two bubbles of the exact same size responding very differently. So the amplitude of the bubble oscillations is quite different. And basically this is explained, or the only way that we can explain this is that they have a different shell viscosity. And that gives these kind of results give us a huge scatter, an order of magnitude scatter of shell viscosities. And we also get no variation with the equilibrium bubble size. Just to compare with a couple of examples from the past, it's a little bit of a different range, and again, a much bigger scatter that has been reported in the past. And the way to really explain this is that it's just bubble to bubble, the kind of the molecular behavior of the lipid monolayer. You have these lipid kind of domains that they differ a lot from bubble to bubble. So there's no way, even if we have the exact same fabrication method, we have the same bubble population, bubble to bubble, the acoustic response is just really, really different. Okay, so just to explain why people in the past have been finding these weird trends, and this clean data is actually related to the measurement error. So it's showing the weakness of experiments. There's been a lot of different sources of error where the error scales with the bubble size. So then you would kind of get a viscosity estimate that depends on the equilibrium bubble size. And this was something that we were able to then demonstrate by kind of adding artificially this error. Anyway, so this is where I don't know anything about molecular dynamics, but I think that there is something that can be done looking at the kind of the molecular behavior of these lipid monolayers, and especially something that currently is unknown is how they respond to extreme fast stretching and compression like we are doing in these bubble systems. And also like, there's currently no experimental techniques to characterize that properly. So that would be interesting. Anyway, going back to the bubble therapy motivation, so we're looking at the acoustic response of this single spherically sort of moving, oscillating bubbles. But now we're interested, okay, so how do they interact with their surroundings? And why do these bubbles allow for sonoporation to happen? Sonoporation means basically creating these pores on cells to let the drugs go through. So to understand the fluid dynamics around it, the physics, why are these bubbles so powerful? There's been quite a lot of efforts in the past, a lot of different mechanisms proposed. So one being microstreaming. So when a bubble oscillates near a boundary, it creates streaming flows, and those can generate shear stresses that are important enough to break lipid vesicles. However, the timescales of this microstreaming are a lot higher than the kind of reports of sonoporation occurring maybe in the microsecond scale, while microstreaming needs millisecond scale. So that's not the explanation why sonoporation has been observed at short timescales. Then we have inertial jetting. So it's similar type of jetting that I showed you earlier with these vapor cavitation bubbles. Certainly can sonoporate and make pores on cell membranes. However, this happens typically at pressures that are so high that they are prohibitive in the clinical setting. So we're talking about megapascal pressures that we can't use in the clinics. And sonoporation has been observed at much lower pressures in vivo and even now in clinical trials. And this is typically in the order of 200 kilopascal pressure for megahertz frequencies. So the question is, what do these bubbles do at this pressure to allow for sonoporation to happen? So fluid dynamics approach, we have this idealized experiment where we look at just a big air bubble in the order of 10 to 100 microns sitting next to a glass substrate and see what happens when we drive it at near resonance. So in this case, to resonate these large bubbles, we're using frequencies of 10 to 100 kilohertz. So this is what happens. This is our experiment. We first have volumetric oscillations. It starts creating shape modes, and these are the standing waves, standing wave patterns forming on the interface. And at some point, a certain amplitude is exceeded, then you can generate jets. And these are repeated jets that hit the substrate cycle after cycle after cycle in a subharmonic manner. So we have axisymmetric shape modes, we have repeated jets, and then eventually the symmetry breaks and the jetting stops. In any case, what I would like to highlight here is that this happens at very low pressures. So it's only 12 kilopascal in this experiment. So it is a relatively gentle driving of these bubbles, but we are generating high-speed jets. So this image shows you a little bit, okay, we can get quite a lot of information, but it's not, we do suffer from optical distortions. We have, you know, it's always kind of typically what we ask ourselves is it better shadowgraphy or diffused light? Where do we get most information, especially how can we see the jet inside the bubble? The way to overcome these optical limitations was to try exploring X-ray imaging. So we brought the experiment to the synchrotron X-ray radiation facility, which is in Grenoble in France. They are specialized, this particular beamline ID19 specialized on ultra high speed imaging, which we obviously like in our setups. Okay, the setup is a bit complicated, but essentially what we leverage is that X-rays, extremely high energy X-rays, and again, needs to be high energy, and that's why we need to go to the synchrotron, because we image at high speeds. So of course, lab X-rays can be also used, but then we can also only look at slow phenomena. So we use X-rays, they would go through our sample, then they hit a scintillator element that converts X-rays into visible photons that then can be captured with a normal high-speed camera. And the beautiful thing about X-rays is that it basically everything in the X-ray beam is in focus. You have effectively infinite depth of field, which is great for us because usually we also it's very challenging to get targets into focus, especially if they're in different locations. Here, everything is in focus. Phase contrast modality, which is not densitometry. It's not, we're not leveraging differences in density, but we're leveraging the fact that every interface is captured sharply with the phase contrast modality. Essentially perturbs these coherent X-rays, and then you get these bands on the image. So we can capture every interface present in the X-ray beam. So for example, if you have bubble clouds or so, every bubble in this cloud would be resolved, while in optical imaging, you would not have access to the middle of the cloud. So just examples of the types of videos we can get with X-rays. So we have ultrasonic drop atomization on the top, this one. So you can see quite well every single drop that is being ejected from this acoustically driven droplets. We have acoustic cavitation under ultrasonic horn. So these are also clouds. This is a laser-induced cavitation bubble collapsing near a boundary and forming a jet. And this is a shock-driven collapse of a bubble that contains a droplet inside. So these are all examples where optical imaging wouldn't allow us to have that information, especially you have systems inside bubbles like here, or you have multi-bubble or droplet systems. And so this is really an exciting technique that we have been able to use. Now, going back to these jetting bubbles driven with low amplitude ultrasound. So here we combine top view optical imaging and side view X-rays. Okay, of course, the resolution is not as good because we are looking at really small scales and we just have to live with the resolution limits. But the beautiful thing with the X-rays is that we can visualize very well the jetting formation, and we can get quantitative information like speeds and so on, onset and things like that. And just for the kind of mechanism behind this jet formation, you may be familiar with the Longet-Higgins jet, which is a jet that forms from standing waves. So this is the same thing. We're forming standing waves on the bubble interface and getting these beautiful jets. So are these relevant to the microbubbles at the microscale? The answer is yes. We can also see this with the contrast agent microbubbles, so these micrometric bubbles. So we're looking at 3 microns, which we now visualize from the side. So this is side view microscopy. I can't even stress how ridiculously difficult it is to do this experiment, but we finally managed to get the bubble info, find the bubbles, get the bubble in focus, and then see how it behaves next to a substrate. We're driving in near resonance. So here the resonance frequency is higher, 1.5 megahertz. And of course, it's not as clear because we are limited by resolution, but the bubble does then respond with volumetric oscillations, has shape modes, and then induces jets that then hit the substrate many times in the same location. So this is why we think that this is really the son operation mechanism, or at least one of the key mechanisms in play. And just to convince you that these tiny microbubbles that are coded also can form shape modes, like the large bubbles that I showed you earlier. Well, these are examples of different degrees of shape modes. That basically is just, you can get to higher degrees when you have larger bubbles, so you can accommodate a larger number of these wavelengths. And you can get those shape modes, and then at higher amplitudes, at many orders will form jets. So this is an example of order 1. Order 2, we have a double jet. Order 3, we even have 3 jets inside the bubble. Order 4 is really barely visible, but there are jets there as well. And the beautiful thing is with these types of experiments, we can then make a parameter space. This is showing the jetting or non-jetting behavior in a space of bubble sizes and acoustic driving pressures. And of course, the easiest jetting happens at the resonance bubble size. So the lowest pressure is needed to induce the jetting. And what I'd like to highlight here is that the clinical pressure window, so 200 kilopascal, most bubbles within this size range, which is the relevant size range for the clinical applications, will be jetting if they are next to a boundary at this pressure. Anyways, I shift gears. Now I'll talk about acoustic droplet vaporization. So this is similar topic, except that instead of using microbubbles, we use micrometric droplets. And now what we leverage is the vaporization of these droplets into bubbles. And then as bubbles, they will have similar sort of properties and features as the microbubbles I mentioned earlier, with the benefit of droplets being that if they're smaller, they can leak outside of the vasculature, they can get closer to the target, tumors or whatnot. And also they don't scatter sound the same way as bubbles, so then they don't distort the ultrasound beam and so. With applications, again, in drug delivery, but also embolotherapy, where you want to block blood vessels, for example, to starve the tumors from oxygen supply, for example. So then these droplets become large bubbles, they can block the blood vessels. The physics behind this phenomenon is a little bit intricate. It's not entirely clear. Why would you vaporize droplets with acoustics? You're not heating them up. So first, of course, you're generating sound waves, then they transmit inside the droplets. They initiate vapor bubble nucleation, and then that nucleation initiates the full vaporization of the droplet. These droplets are superheated. They would like to be in a bubble gas state, but you need a little bit of acoustic energy to then initiate this phase change. So the way that we look into this experimentally are the similar setup as mentioned earlier, with ultra high-speed video microscopy, and the types of images we get are like this. So this is a droplet being hit by an acoustic wave, and then you basically create a small cavitation bubble inside the droplet, which initiates the phase change. And what's interesting is that the location of this vapor bubble is very deterministic. It's very, it's always in the same location. It's not at the center either. And that can be explained by, if you're looking into the acoustic transmission inside the droplet, it's not completely straightforward. The droplet is a lot smaller than the wavelength of the input acoustic waves, but here you can see lobes of tension, which might explain it. And indeed, if you then compare the location of the nucleation spots with the minimum pressure feed, or the minimum pressure that you can achieve inside the droplet based on these K-wave simulations on MATLAB, then there's a pretty good agreement on the location. So now the question is, how does this tension actually get generated? So this is a theoretical, showing theoretical analysis on how the dashed line is the input wave, how it gets distorted by the presence of the droplet that acts as an acoustic lens. And you can see it's a little bit complicated. There's some kind of a weird resonance behavior, and also a lot of tension. There's a huge tension peak that appears where the cavitation bubble then forms. And to get a little bit more insight into this, we decided to look at the compressive part and the tensile part of the ultrasound wave separately. And so basically what happens there is we see that when we only send a tensile wave, it gets amplified a little bit by the droplet, which is basically what we expect, but not enormously. What is more surprising is that if we send a purely compressive wave, it also generates tension. What I would like to highlight here is also the mismatch between the acoustic impedance between the droplet, the liquid inside the droplet, and the surrounding water is not such that the phase change would happen at the reflection of the boundary. So there's something else coming into play. And indeed, if we look at this, is again a K-wave simulation, so it's a K-space pseudo-spectral method with the MATLAB toolbox. We send a Gaussian compressive wave, again, only compressive wave. We send it to the droplets. And indeed, we see that there is tension being generated at the focus. So the wave, this is a plane wave, Gaussian plane wave that focuses inside the droplet, and there is tension after the focus. And then if we look at then the kind of negative pressure amplification areas, we see that indeed the largest tension happens after the focus. So this, okay, there's actually a lot of very interesting physics coming into play, and something we believe it's caused by the GUI phase shift, which is something known in optics. We know in optics, if you focus waves, they can change phase. It's less known in acoustics, but apparently this happens. It's very, very interesting. Basically, message here is that if you're focusing compression waves, they can change phase and become tension waves just because of the focusing. To check this hypothesis, we experimentally send only compressive waves. And we can do this by generating shock waves. And we generate shock waves by focusing a laser, generates a little plasma inside the water, and that plasma expansion generates a shock wave. Very sharp, but mostly compressive. It has a little bit of a tensile tail, but we send a compressive wave and see if we can generate cavitation. And this is a shadow graph imaging of that. We can see that there is indeed nucleation happening. Of course, we are limited by optical imaging, so we also bring to the X-ray facility, and we see that we can generate cavitation inside the droplet with only compressive waves. And then a beautiful thing is we can then compare the location of the biggest tension amplification we get, and they match very well with the experimental nucleation spots. The consequence of this,
what's really interesting about that is that you can send ultrasound waves that have a more energetic compression part compared to the tension wave. It's medical applications are limited by the tensile amplitude of the ultrasound waves, because you might cavitate inside the body, so you have to reduce the amount of tension you send to the body. But now we basically, with this, we can send more compression, and if that helps vaporize the droplets, then we can make the ultrasound treatment safer. So comparing a transducer where we have kind of similar compression to tension amplitudes, and then a very distorted waves where we have more compression and tension, and then we can look at the threshold peak negative pressure at which the vaporization happens, and we can see that with the distorted waves, this threshold is reduced drastically, which is very interesting for biomedical applications because we want to reduce the negative part. Now, and the future outlook is we're trying to also experimentally have a look at these pressures inside the droplets and also experimentally prove the phase change. And we do this by doing background-oriented Schlieren. So we look at this is a droplet and has at the back a reference pattern. And we look at the displacements of this pattern features. With the passage of the shock, and the displaced because of a local change in refractive index in the medium. And then we haven't extracted the pressures yet, but at least we're getting displacements really nicely. And then hopefully with that, we can also get pressure measurements inside the droplet, which is kind of the thing that we're currently lacking experimentally. But where simulations, of course, help. So now this concludes my talk. Main take-home messages are relating to the initial goals that I mentioned at the beginning of the presentation. Can simulations help compensate for experimental limitations? Answer is yes. Of course, the pressure fields are the main problem that we can't really measure, despite my final efforts that I mentioned, but of course they also have limitations. We need the pressures. I'm particularly interested in the molecular behavior of lipid monolayers in these extreme stretching compression conditions. Prediction of phase change and vapor nucleation is something that also a lot of simulation efforts can be made there to model that. And then, of course, something I didn't talk about was bubble cluster behavior, but it's experimentally, of course, we can observe them, but there's very little order and control we have in the configuration. So that's something simulations can help, is having controlled initial conditions with a lot of bubbles and droplets, and then you can see the interactions and predict how they behave collectively. And then the second one is I'm hoping that I have been able to present some unique experiments that could be useful for numerical validations and benchmarks. And in particular, something that we've been trying to push is ultrafast video microscopy, high-speed imaging at microscale, and also this synchrotron X-ray phase contrast imaging, especially for multi-phase flows and for multi-phase systems. This is particularly interesting. And just like to thank, these are the two doctoral students who are really leading the work that I presented today. And of course, the team at ETH and collaborators. And then especially, I thank you for your attention. I'll be happy to take your questions.
So we have some time for questions.
I'm curious about the mechanics of the monolayer that you discussed. So I think in your model, it seems you have the stretching part, but I'm just wondering if you have to think about bending as well.
Yes, yes, for sure. Absolutely. And I mentioned, that's a good question. I mentioned at some point that the shell buckles. It cannot, I mean, there's a question is that can the shell withstand compression? And it's experimentally, we are at the limit. We cannot tell. It looks like it might not, but we basically pixel limitation. Within the pixel limitation, we don't know which radius does the buckling initiate. So we can't tell. But yes, it becomes relevant.
I wonder if that might explain some of the fusion difference of bending size.
The shell viscosity could very well be, could be, but can't tell. Thank you.
Basically the same question, but maybe in addition, if you would do a macroscopic experiment, something like an annual graph, you already get information of the?
Very good question. We would love to. The problem is that the scale and the speeds. There's no way we can excite in those experiments at these rates. We are looking at megahertz excitation, stretching, compression, stretching. So no, we cannot. The lipid monolayer is expected to behave very differently. Thank you. Right. Very good questions. Thank you. First question: acoustic radiation forces. Yes, they're omnipresent. They make the bubble. They move the bubbles. The bubbles they translate because of the acoustics. That's a primary acoustic radiation forces. Then you also have the secondary one whenever there are multiple bubbles or boundaries. So then you have the secondary, acoustic sources, if you will, that definitely affects the dynamics. That's why we're trying to isolate our bubble as far as possible from all sources. And also in this case, the acoustic radiation forces, the displacements from them, they're still within those very short ultrasound bursts that we look into. They're quite small. But if you have longer bursts, yes, the bubbles displace with the acoustic waves. Exactly. And actually, I have an example of acoustic radiation forces, these weird shrimp-looking structures. This is time, it's kind of overlapped frames from cavitation bubble clouds that are actually very small. So the cloud at an instantaneous cloud is maybe this size. And then, but this is time average. So this length of this shrimp corresponds to an acoustic burst length, and it moves. So that's acoustic radiation force. Now the second question related to the acoustic scattering. Yeah, people use this. You get this from populations, and so getting this from a single bubble is a challenge, and this is a challenge that we want to tackle. It's very difficult to get a clear acoustic signal from a single bubble activity, but the idea is that we'd like to correlate that to the collective behavior of bubbles that you do this acoustic scattering measurements. But yes, it's quite standard. A lot of people use it. So, thank you.
Thank you again for that.
Oh, it's ridiculous.
Okay, there's something.
I'm not the first person to complain.
My pleasure to announce the talk of Professor Tucci, from Tauro. Currently from where? Sauro once told